So, continuing on with the Chapter 1 lecture for Chem 112, we're going to be discussing now constitutional isomers and stereoisomers. So, stereoisomers are structures with the same formula in which atoms are bonded with the same connectivity but with a different three-dimensional shape. So structures with the same connectivity, same formula, but a different three-dimensional shape are known as stereoisomers. There are a few examples of stereoisomers. One example concerns tetrahedral centers, where we have, in this case, these two stereoisomers of the following molecule. Whereas you can see the carbon is still connected to the same atoms, chlorine, bromine, iodine, and hydrogen. However, these two molecules have different three-dimensional shapes. The second major example of stereoisomers concerns the geometry of alkenes, also known as carbon-carbon double bonds. As you can see, looking at these two structures, even though the carbon in each of these structures is connected to a chlorine, hydrogen, and double bond to the other carbon, the overall three-dimensional shape, the arrangement of the chlorines in three-dimensional space, is different for these two stereoisomers. These are known as cis and trans alkene stereoisomers. We will talk more about stereoisomers in later chapters. Constitutional isomers, on the other hand, are structures with the same formula, but the atoms are bonded with a different connectivity. So an example of this is looking at a nitrile versus an isocyanide. So here is what a nitrile looks like. This is acetonitrile. However, for this same formula, we can draw a constitutional isomer which has the same formula but a different connectivity. This is known as an isocyanide. And in terms of being able to tell these two apart, if you had a sample of a nitrile and an isocyanide, you'd be able to tell them apart almost immediately in the laboratory, as isocyanides are incredibly foul-smelling compounds. So in this case, as you can see, these two compounds with the same formula and different connectivity, these two constitutional isomers, are easily distinguishable, and it's important to be able to identify constitutional isomers because oftentimes when you're given a formula, be it as part of elemental analysis or another characterization technique, it's important to be able to draw multiple plausible structures for a given formula. So let's look at an example where we're asked to draw a constitutional isomer for the following molecule and draw a stereoisomer for the following molecule of C2H2Br2. So I'd like you to pause the video at this time and work through this example, and then we'll discuss this example momentarily. So I'll give you a few moments for that, and then we'll discuss. So first and foremost, given that we already have a valid Lewis structure, if I wanted to draw a constitutional isomer, I need to have the same formula but a different connectivity. So what I'm going to do is I'm just going to move one of the bromine atoms from one carbon to the other. Note, I really don't want to swap the position of the bromine atom on the same carbon because that's going to be a way to get a stereoisomer, as we'll see in a moment. So this is a constitutional isomer. As we have the same formula, but a different connectivity. Let's now draw a stereoisomer. So a stereoisomer, we want the same formula, same connectivity, but a different 3D shape. So to this end, let's take one of the bromine atoms on one carbon, and let's move it to the opposite position on the double bond while keeping it connected to the same carbon. So this gives us the following stereoisomer. So here we have the trans stereoisomer of this alkene. Let's draw the cis stereoisomer. So we've now drawn out a constitutional isomer and a stereoisomer for the following molecule. Wonderful. So let's look at another case in which we're asked to identify which of the following structures are constitutional isomers, and then we're asked to draw another constitutional isomer. Okay, so just as a reminder, constitutional isomers are a pair of molecules with the same formula but a different connectivity. So if I look at this molecule in the middle, I can see that the molecule on the right is just the exact same molecule, just rotated. We have the same connectivity, a carbon attached to carbon, 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 and oxygen, and an oxygen attached to a carbon and a hydrogen. So we can immediately cross this one out. And as you can see, looking at the structure on the left, if we compare these two structures, we have the same formula, we have the same number of carbons, same number of hydrogens, same number of oxygens. However, we have a different connectivity. Now, if we wanted to draw another constitutional isomer, so we want to make sure we have the same formula, but we have a different connectivity of atoms. One easy way to do that is to simply move a group over and change the connectivity of atoms. So for example, this CH3 group, I'm just going to move it over and have it attached to this carbon instead. So this gives us a CH3 group. We have a CH2 group now. Then we have a CH group, a CH3 group, and our alcohol, which is an OH group. So as you can see, we've kept the same carbon count. We still have 4 carbons. We still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens and an oxygen. We've just moved the position of this CH3 group over. So we've changed our connectivity while keeping the formulas the same. So this is one constitutional isomer that we've drawn for the following molecule. Okay, let's now talk about one way of representing organic structures. These are known as condensed structures. So in condensed structures, the carbon-hydrogen and carbon-carbon single bonds are not drawn. Carbon-carbon double and triple bonds are drawn, while all other double bonds are not drawn typically in condensed structures. So for example, looking at 2-methylbutane, the condensed structures for 2-methylbutane, rather than drawing out all the carbon, hydrogen, and carbon-carbon bonds, we instead abbreviate each group. For example, this collection of carbon and 3 hydrogens would be abbreviated as CH3. This collection of carbons and 2 hydrogens would be abbreviated as CH2. We still designate connectivity either by explicitly drawing the group connected to each carbon, such as in this case where we drew this connected CH3 group, or via using a condensed formula where we note that this carbon here is attached to 1, 2 CH3 groups, and thus why the subscript is used. For other types of double bonds, such as that found in an aldehyde, this entire collection of atoms, which contains a carbon-oxygen double bond, and the carbon is attached to a hydrogen, we abbreviate it using a defined abbreviation. So this CHO abbreviation is telling us we have a carbon double bonded to oxygen with that carbon attached to a hydrogen as well. And this is known as an aldehyde. Now, importantly, when you look at condensed formulas, if a portion of the formula has a subscript, the subscript indicates the number of formula subunits attached to the carbon chain. In general, the carbon containing a functional group or an attached formula subunit, such as a carbon chain, will have less hydrogen atoms than an unsubstituted carbon. Further, in cases where a formula unit is repeated, it will be abbreviated using a subscript. So looking at this case, if we have a CH3 group and then a CH2 with a Subscript of 2 followed by CH3. That tells us that we have a CH3 group. Attached to that CH3 group is a CH2 group followed by a second CH2 group. The subscript 2 tells us there are two CH2 groups, also known as methylene groups. Finally, at the end, we have a CH3 group. Looking at this idea of what happens if we have multiple things attached to a carbon, in this condensed formula, we have a CH3 group. Attached to that CH3 group, we have another carbon, except this time that carbon has three OH groups attached to it, which we draw as such. Notice in this case, one way that we can tell that this carbon has the OH or hydroxyl groups attached to it is the fact that it has less hydrogens than usual. Okay, now you've begun to start to hear names of these various what are known as functional groups, which are specific groups of atoms with unique reactivity. For example, a carbon-carbon double bond is known as an alkene, a carbon-carbon triple bond is known as an alkyne, and a collection of carbon-carbon double bonds arranged in a ring are known as an arene group. Now, alkanes have a carbon-carbon single bond, alkenes have a carbon-carbon double bond, and alkynes have a carbon-carbon triple bond. Condensed formulas are very useful as they clearly indicate the functional group. And I prepared an appendix of various functional groups. Here's an example of what this appendix looks like. We have the functional group, an example structural formula, a condensed formula, as well as some information on the name and oxidation number calculations. We're not going to be going through each of these functional groups in detail right now, but I would encourage you to start to familiarize yourself with the different functional groups found in these note sets, as we will be seeing these functional groups a lot throughout the future chapters. So there are two appendix pages of all the various functional groups that you'll encounter. What we're now going to do is practice writing some condensed formulas. And once we write out the condensed formulas, we'll identify the functional groups in each structure. So what I'm going to do is I'm going to do the first three examples, and then you'll do the next three. So in this case, first and foremost, let's look for repetition. So in this case, we have 1, 2, 3, 4 CH2 groups. So we can write this formula as CH3, CH2, subscript 4, CH3. The only thing in terms of functional groups that's present are alkane. This molecule would be called an alkane, as it just has carbon-carbon and carbon-hydrogen bonds. Looking at this next structure, we have a formula of R, which is any alkyl group, any carbon-hydrogen group, O, which is an oxygen atom, followed by R, which is any alkyl group once again. This is known as an ether. So this collection of atoms is known as an ether. One thing that I'd like to draw your attention to is the fact we have repetition. We have CH3, CH2, followed by O, CH2, CH3. Notice this CH2, CH3 group is repeated. So what we're going to do is we're going to abbreviate that with a subscript of 2. Now, looking at this last case, we have the R, which is just an alkyl chain attached to an OH group. This is known as an alcohol. Writing a condensed formula, we have a CH3 group followed by a CH group. The OH group is attached, so we put in an abbreviation, OH, followed by CH2CH3. Whenever you have a group attached in the middle of the chain, you can note that by putting that given group in parentheses. Now that you've seen these representative examples, I'd like you to attempt to write out the condensed formula for the following three structures. Keep in mind, carbon-carbon double and triple bonds are noted in the condensed formula. So we'll take a few minutes for you to work through these examples, and then we'll discuss. So let's take a look at this next case. An R followed by a CN group. This is known as a nitrile group. This group here is the nitrile. So we'd abbreviate this molecule as CH3CN. In this case, the carbon-nitrogen triple bond is implied from the formula. Looking at this next case, we have a CH3 group followed by a carbon-carbon double bond, CH double bond CH, followed by CH3. In this case, you would not abbreviate it even though there is repetition because there's a carbon-carbon double bond separating and it's not entirely symmetrical across the double bond. Looking at this final case, this RCO2H group is known as a carboxylic acid. So we'd abbreviate this molecule as CH3CO2H. Okay, let's look at another case. In this case, we're asked to write the Lewis structures from the condensed formula. So here we're asked to draw the Lewis structure for the following condensed structures and name all functional groups. I'll do the first example, you'll do the next two. So in this case, we have CH32COH. So I'm going to write out my CH3 groups. These two CH3 groups are attached to our central carbon. How can we tell? That carbon has way less hydrogens than usual. Also attached to this carbon are two OH groups. So in this case, the functional group that we have is an alcohol. When you have a carbon attached to these two oxygen atoms, this looks very similar to a functional group that we'll talk about later, which are acetals and hemiacetals. But in this case, we don't have the exact connectivity matching that functional group. So it's fine for you to label this as just an alcohol. Importantly, whenever you encounter complex functional groups, please do not break a complex functional group into pieces. Look at the functional group as an entire collection of atoms. So with this initial example in mind, I'd like you to work through the next two examples, draw reasonable Lewis structures given the condensed formulas provided, and then I'd want you to name all the functional groups found in the molecule that you prepared. So we'll discuss this example momentarily, so pause the video and work through this example, and then we'll discuss. Okay, so looking at this next case, we have CH3CHO. There are a few things to keep in mind here, and there are a few things that I'd like to point out that you need to pay special attention to. First and foremost, this CHO group tells us that this carbon has a double bond attached to it. This is a signpost for an aldehyde. You can also tell because this carbon has less hydrogens than it would usually have if it were just a complete normal straight chain carbon. So we write out our CH3 group, and then we write out the aldehyde group, which is a carbon-oxygen double bond and a carbon attached to a hydrogen. So this entire functional group is known as an aldehyde. Okay, let's look at this next case, CH3CONH2. This entire collection of atoms is a signpost that we have what's known as an amide. So we write out our CH3 group, and for an amide, we have a carbon-oxygen double bond, followed by connection to a nitrogen atom with two hydrogens attached. And this entire collection of atoms shown here is an amide. So we're starting to familiarize ourselves with condensed structures and condensed formulas and various functional groups. Let's now tackle some bond line structures. So in bond line structures, bonds are drawn in a zigzag format, with each line representing one bond. What do I mean by that? If we are writing a straight carbon chain, you're going to want to make sure that your carbon-carbon bond angles, looking at the bond angle between carbon atoms, is about 109 degrees, because the carbons are tetrahedral in most cases. The start and end of a line represents a carbon atom, which is not shown, or whatever atom symbol is shown, such as oxygen or nitrogen. Importantly, in bond line structures, all atoms have hydrogen atoms needed to have the correct formal charge and a complete octet, with carbon typically having 4 bonds. Lone pairs are typically shown in bond line structures. So, for example, if I drew this line here, each point on the line would represent a carbon. And by the same token, each carbon atom would have sufficient implied hydrogens to fulfill its octet. So that line that we've drawn would represent 2 carbons, each bonded to each other with 3 hydrogens attached to each carbon. I prepared a little table which summarizes the bonding preferences both for various charges of a given atom, such as carbon, nitrogen, oxygen, sulfur, and phosphorus, as well as the general number of bonds and lone pairs each given atom prefers to form. Now, importantly, I just want to reflect again that bonds are drawn to reflect the geometry of the molecule. Single bonds are drawn in a zigzag format. So for example, CH3, CH2, CH3 would be drawn as one line for the first 2 carbons and a third line for the third carbon. So as you can see, we have 1, 2, 3 carbon atoms, and we've made sure to preserve the fact that carbon is tetrahedral, so this bond angle is about 109 degrees. Likewise, CH3OCH3, which is dimethyl ether, would be drawn out as a line connected to oxygen, followed by another line connected to oxygen. We then include our lone pairs. This structure is equivalent to saying we have the following full Lewis structure. The reason why we choose to use bond line structures is that they're more efficient at conveying a structure without requiring us to draw out every single hydrogen atom. Importantly, double bonds are drawn with 2 lines. So for example, CH2 double bond CH2 would be represented in bond line notation as so. CH3CHO would be represented first with 1 line representing our first 2 carbons, and then attached to this carbon is a carbon-oxygen double bond, like so. We then add our lone pairs, and this completes the depiction of the following compound. Note, even though it's not entirely correct, in many cases, if you have an aldehyde, the hydrogen will be drawn for the aldehyde. Triple bonds are drawn with 3 lines and are linear. So for example, C2H2 or acetylene, which is represented like so, would be depicted in bond line notation as just 3 lines, which imply there's a carbon triple bonded to another carbon. Likewise, CH3CO+ would be represented as 1 line for the first 2 carbons, and this carbon-oxygen triple bond would be represented by 3 lines followed by an oxygen atom. The oxygen atom has a lone pair and a formal charge of +1. This is equivalent to the following Lewis structure. As you can see, bond line structures are incredibly succinct and efficient. So let's talk about some common mistakes. If a carbon has a formal charge, you'll want to make sure to indicate the formal charge and add the appropriate number of lone pairs. So for example, this carbon has a -1 charge, so we need to add a lone pair in order to ensure that the formal charge of this carbon is correct. So let's see, 4 minus 3 bonds plus 2 lone pair electrons gives us a formal charge of -1. So adding this lone pair is needed for this carbon to have a -1 formal charge. Likewise, if we look on the right, we have a carbon with a -1 formal charge. Adding a lone pair gives us the correct displayed formal charge because 4 minus 3 plus 2 gives us -1. Importantly, when drawing double bonds, make sure to draw the bonds as far apart as possible, ideally with a 120-degree angle separating atoms. So for example, if we wanted to make a condensed structure of the following molecule, we draw NH2, O, then a carbon-carbon double bond, followed by a CH3 group, which we don't write out the full CH3, and then our OH group. We then add in our lone pairs, and this gives us the correct structure. As you can see, when we look at this carbon-carbon double bond, the bond angle across the carbon-carbon double bond is close to 120 degrees. Additionally, you'll want to make sure to draw out all of the non-carbon atoms, and you're going to want to make sure each non-carbon atom has the correct number of lone pairs and hydrogens as depicted in the original structure. The last thing I want you to note, please don't change the double bond geometry. Anytime you have a carbon-carbon double bond, draw the position of substituents across the double bond exactly as it was in the original structure. Finally, all heteroatoms must be drawn with the appropriate amount of lone pairs, and all hydrogen atoms attached to heteroatoms must be drawn. So for example, in CH2CHOH, in this case, we have implied, in this case, a functional group. So this CH2CHOH in this formula, writing it out, we have a CH2 group connected to a CH group connected to an alcohol. So this is our preliminary Lewis structure. Converting this to a bond line format would look something like this. Looking at this next case, CH3CONH2, just drawing out a preliminary Lewis structure, we have a CH3 group and then an amide. Converting this to a condensed structure, we draw out one line for this first set of carbons, then we draw out our carbon-oxygen double bond, and then we draw out the amine group, which has 2 hydrogens and a lone pair. Now, if an atom is sp hybridized, you're going to want to make sure that the bond angles are 180 degrees. In some cases, an ambiguous carbon is represented by a dot. So looking at CNO, in this case, we have a carbon, a nitrogen, and an oxygen. This is actually another functional group, but it's a more obscure functional group. In this case, if we draw out a complete Lewis structure, we would get a Lewis structure that looks something like this, with a total charge of -1. Now, from here, converting this into a bond line structure, the carbon is implied, the nitrogen and oxygen are drawn. And that gives us the following bond line structure. In this case, you don't really get that much efficiency by abbreviating the carbon atom. One thing I do want you to note is because this central nitrogen is sp hybridized, this bond angle is 180 degrees. Looking at this next case, CH2CO, this has a Lewis structure, which looks something like this. If we wanted to abbreviate this structure in bond line notation, we draw our carbon-carbon double bond, and then we draw our carbon-oxygen double bond. Now, it's a little ambiguous what's happening with that central carbon, so oftentimes a dot will be drawn. This specific functional group is known as a ketene, and the carbon variant is known as an alene. You don't need to memorize that, but anytime you see this dot notation, it's important to note that it's representing what would be an otherwise ambiguous carbon. Okay. In terms of drawing Lewis structures from bond line structures, there are a few common mistakes. Carbon typically forms 4 bonds. So after adding hydrogen atoms to each atom to reach a complete octet, please make sure to check that the formal charges on each atom matches the formal charge in the structure. So for example, if we are writing out and starting to expand these bond line structures into Lewis structures, you want to make sure that each carbon has a complete octet and that the substitution pattern on each atom gives the correct formal charge. So for example, here, let's start by explicitly writing out all of the carbons. That's the first step that I like to use when I'm expanding out these bond line structures. From here, I will fill in lone pairs and hydrogens to give us a complete octet. So I'm adding in my implied hydrogens. And if a lone pair is present on any carbon, you'd be able to see that in the original bond line structure. So I'm just slowly adding in hydrogens to each carbon such that it has 4 bonded atoms or lone pairs attached to it, such that it has a complete octet, unless indicated otherwise by a formal charge or something else in the bond line structure. In this case, there's no unique formal charge on any of our carbons, so we're just filling in hydrogens to give us a complete octet. Looking at this next case, I'd like you to take a moment and work through this next example. So in this case, we have the following bond line structure, and I'd like you to try drawing out the full Lewis structure. So I'll give you a few moments to work on that, and then we'll discuss. Okay, so looking at this case, as always, first thing we're going to do is we're going to draw out all of our carbons. So every point on a line, every junction on these bond line structures represents a carbon. From here now, we're going to fill in our hydrogens such that we have a complete octet. So this carbon has 2 bonds and needs 2 more to have a complete octet. These carbons, as part of the triple bond, already have a full octet. They're good to go. This carbon has 3 bonds. It needs 1 more hydrogen. This carbon on the far end has 1 bond. It needs 3 hydrogens. Okay, let's look at some case studies now. Let's try to draw out some Lewis structures from both bond line and condensed structures. So I'd like you to take a few minutes to work on the following two examples, and then we'll discuss. I would encourage you to pause the video to work through these examples over a little bit more time, and we'll discuss momentarily. Okay, so looking at these examples, first and foremost, we have some atoms with formal charges. So we're going to want to make sure that our final structure with all the lone pairs added in has the correct formal charge. So let's draw out all of our carbons. From here, we're going to add lone pairs such to give a complete octet or the correct formal charge to all of our non-carbon atoms. For our carbon atoms, we're going to add implied hydrogens such that it would give a complete octet. This carbon here has 4 bonds, so we don't need to add any additional hydrogens. This CH3 group needs 3 hydrogens in order to have 4 bonds and a complete octet. Looking at this second case, we have CH3CH2, OCH2, CO2H. So we have an ether and we have a carboxylic acid. This is where recognizing functional groups is going to be incredibly useful. Because we have a condensed formula, we can often just read this condensed formula from left to right. So we have a CH3 group, a CH2 group, an ether, another CH2 group, and then a carboxylic acid, which is CO2H. Now, if you wanted to clean up this structure, you'd want to make sure that the bond angles match the geometry, but this is fine for now. We've adequately expanded out the condensed formula into a Lewis structure, which we can then interpret further. So we've seen how to draw bond line structures, how to write condensed structures, and how to convert bond line and condensed structures into Lewis structures. So it's important to be used to drawing bond line structures, as that's going to be the primary way that we're going to draw and talk about structures moving forward. Okay, what we're now going to talk about are some factors related to bond length. So bond length decreases with, in order of importance, increasing bond order, which means double and triple bonds are shorter than single bonds. For example, a carbon-oxygen double bond is shorter than a carbon-oxygen single bond. Bond length also decreases with decreasing atomic size. The smaller the average atomic radius, the smaller the bond length. For example, an HF bond is shorter than a hydrogen-chlorine bond. As a refresher, atomic radius increases as you move down a group and left across a period. Here's an example table containing atomic radius in the periodic table. Generally, as you move down the periodic table, down a column, your radius increases. And as you move down and to the right of the periodic table, your radius, as you move to the right on the periodic table more specifically, your radius decreases across a row. So when we're looking at different bonds, let's answer this question. Which of the following bonds are shorter? I'd like you to pause the video and work on these examples, and then we'll discuss momentarily. Okay, so here we're comparing a nitrogen-oxygen double bond and a nitrogen-oxygen single bond. Double bonds are generally shorter than single bonds. Comparing a hydrogen-bromine and hydrogen-fluorine bond. Fluorine is smaller than bromine, so the hydrogen bromine hydrogen, sorry, so the fluorine is smaller than bromine, so the hydrogen fluorine bond should be shorter. Next, we have a hydrogen bromine bond versus carbon fluorine. Hydrogen is small, but bromine is very large. So the carbon fluorine bond, looking at our atomic radii, we have radii lengths of 77 and 72. For hydrogen and bromine, we have 114 and 37. Now in this case, because bromine is so large, this hydrogen-bromine bond is going to be longer than the carbon-fluorine bond. When you're thinking about bond length, you want both atoms to be small and close in size. This gives you a shorter overall bond length if the atomic radius of each atom is small. When you have one atom that's especially large, that one atom's atomic radius is often going to make the overall bond length quite long. So, in general, double and triple bonds are shorter than single bonds. Small atoms make short bonds. Okay, let's talk about another property of bonds, which is bond enthalpy. Covalent bonding is favorable because bonding electrons are stabilized by nuclear charge. Again, we can take our bonding electrons, and these bonding electrons are stabilized by the nucleus of each atom participating in the bond. As a consequence of this, breaking chemical bonds costs energy, and this is known as the bond enthalpy. These bond enthalpies are homolytic, which implies an even break of the bond to yield radicals. Heterolytic bond breaking will be discussed later. In general, bond energy and bond enthalpy increases with, in order of importance, bond order. Triple bonds take a lot of energy to break, more so than double bonds, more so than single bonds. An example of this is if we look at the bond enthalpies in carbon monoxide, formaldehyde, and dimethyl ether. The bond enthalpy required to break the carbon-oxygen bond in carbon monoxide, which is a triple bond, takes a lot more energy than breaking the carbon-oxygen single bond found in dimethyl ether. One thing I would like you to note is that in general, breaking just the pi bond requires less energy than breaking a sigma bond. But whenever you break a double or triple bond, you're going to have to break all the bonds. And breaking all of these bonds requires a lot more energy than just breaking a single sigma bond. Now, another factor that affects bond enthalpy is bond length. Shorter bonds are stronger. A carbon-fluorine bond is going to be stronger than a carbon-chlorine bond because the carbon-fluorine bond is shorter. And it's also more polar, which is another factor that's minor. So in this case, we have another comparison in which we're asked which bond is stronger. So I'd like you to pause the video, work through these examples, and then we'll discuss. Okay, so first we have a carbon-oxygen double bond versus a carbon-oxygen single bond. The double bond is way stronger. Next, we have a nitrogen-oxygen bond versus a nitrogen-fluorine bond. Fluorine is smaller, and this bond overall is much more polar, so this bond is much stronger. Next, we have a carbon-hydrogen versus a carbon-carbon bond. The carbon-hydrogen bond is way shorter, and in general, it's pretty hard to break carbon-hydrogen bonds under normal circumstances. These bonds are relatively strong. Okay, let's now talk a little bit about bond length, bond enthalpy, and orbital effects. And this really ties everything together that we've been discussing. Bond strength is based on the relative energy of orbitals used to form a bond. As orbital energy increases, bonds formed using that orbital become less stable. They're weaker. As we discussed previously, the more s character a hybrid orbital has, the shorter and lower energy that orbital is. So in this case, if we compare an sp3 versus an sp2 versus an sp orbital, the sp orbital is the lowest energy hybrid orbital, while the sp3 orbital is the highest energy hybrid orbital. In terms of bond strength, sp bonds made with an sp hybrid orbital are going to be shorter and they're going to be stronger than bonds made with an sp3 hybrid orbital. In terms of bond length, bonds made with an sp hybrid orbital are shorter, while bonds made with an sp3 orbital are going to be longer. So again, just to summarize, sp hybrid orbitals can be used to make short, strong bonds. While if we compare that to an sp3 hybrid orbital, these bonds are longer and they're generally going to be weaker bonds. So the hybridization of the atom used in a given bond and the hybridization of the orbital used to form a bond has a huge impact on bond length and strength. For example, if we look at methane, ethane, ethylene, and acetylene, looking at the carbon-hydrogen bond, a carbon-hydrogen bond made with an sp3 orbital has this bond length and this bond strength. If we compare that to the carbon-hydrogen bond in acetylene, which is made with an sp carbon hybrid orbital, we see that the bond strength increases pretty dramatically as you move from an sp3 to sp hybrid orbital, and the bond length goes down a non-negligible amount. Generally, these orbital effects have a much larger effect on relative bond strength compared to bond length. So in general, the more S character your hybrid orbital has, the shorter and stronger the bond involving that orbital will be. So let's apply what we've learned here, and I'm going to do the first example, you'll do the second. So in this case, we're asked, what is the hybridization of each carbon atom in CH2O and CO2? Here are the Lewis structures for these two compounds. In this case, this carbon atom in formaldehyde, we have 3 bonded atoms. So this would be sp2. The central carbon in CO2 would be sp. So in this case, which bond is stronger, the CO bond in formaldehyde or the CO bond in CO2? In this case, the hybridization of the carbon in formaldehyde is sp2, while the hybridization of the carbon in carbon dioxide is sp. So this carbon-oxygen double bond will be shorter plus stronger because the carbon in carbon dioxide is sp hybridized. The orbital has more S character, so as a result, the bonds formed using that lower energy orbital are going to be shorter and stronger. Let's look at this next example. In this case, we're asked, what is the hybridization of each carbon atom in C2H4 and C2H6? And we're asked, which bond is shorter, the CH bond in C2H4 or the CH bond in C2H6? So I'd like you to pause the video at this time and work through this example, and we'll discuss this example momentarily. Okay, so first let's get some Lewis structures going. C2H4 looks something like this. This is a typical formula for ethylene. C2H6 is our good old friend ethane. Looking at the carbon in ethane, this carbon is sp3, while the carbon in ethylene is sp2. So if we compare an sp2 CH bond versus an sp3 CH bond, generally The sp2 hybridized carbon will have shorter and stronger bonds, assuming the same bond order. So, which bond is shorter? The sp2ch bond found in ethylene is going to be shorter than the CH bond found in ethane. So as you can see, part of the reason why we spent all this time talking about hybridization is in part because hybridization and orbital effects have an influence on bond length and strength, and it's important to consider hybridization when you think about the overall reactivity and behavior of the molecules that you're looking at. So this concludes chapter 1. We've gotten really familiar with drawing structures, portraying structures using bond line, condensed structure, and other methods of structure notation. We've talked about constitutional isomers and stereoisomers, and we've begun to start to look at how a molecule's given arrangement of atoms, be it the hybridization of the atoms and the exact connectivity of atoms in a structure, influences bond length, bond strength, and other factors relating to chemical reactivity. This concludes our discussion of Chapter 1, and we'll be moving on to future chapters as part of the next lecture series.